Annapolis, Maryland, May 1945. Dr. Robert Goddard stood silently inside a naval laboratory warehouse, gazing at the machine before him. The frail physicist, whose voice had been reduced to a rough whisper by the throat cancer that would soon take his life, gently traced his hand across the cold aluminum exterior of the German V-2 rocket. For 2 decades, he had been almost completely alone in the United States, advocating for liquid fuel rockets and struggling to advance his work with minimal funding, while the government paid little attention to his warnings and ambitions. But now, in this dim warehouse, surrounded by Army Ordnance personnel and Navy engineers, Goddard was confronted with a painful realization that would linger over American rocketry for years to come. Germany had not simply built a rocket, they had established an entire industrial ecosystem dedicated to rocketry, and the United States had failed to keep up. As Goddard examined the 46-foot missile towering in front of him, he had no idea that what the Americans would uncover inside this weapon would expose a technological gap so enormous that the United States would spend the next decade and a half fighting to catch up. The V-2 was not just more advanced than anything America had produced. It incorporated technologies that did not yet exist in the United States, solved engineering challenges American scientists had not even fully identified, and demonstrated manufacturing accuracy that American industry was not capable of matching. This rocket was undeniable proof that while America had Robert Goddard experimenting on his own, Germany had Peenemünde. A massive research center filled with thousands of experts, virtually unlimited funding, and 7 years of focused development on ballistic missile technology that would ultimately transform both warfare and humanity's reach into space. The revelation that the United States was dangerously behind in rocket development did not begin in that warehouse in May, but weeks earlier, in April, when American soldiers advancing through Germany discovered something that would alter the course of world history. On April 11, 1945, in the Harz Mountains of Germany, troops from the U.S. 3rd Armored Division descended into the Mittelwerk, underground factory near Nordhausen. They expected another standard military production site. Instead, they stepped into a staggering industrial operation hidden deep beneath the mountains. Endless tunnels stretched for miles. Along assembly lines sat partially completed V-2 rockets at different stages of production. Nearby, warehouses overflowed with components, and rooms were filled with technical papers and blueprints. And throughout the tunnels lay the horrifying evidence of forced labor, starving prisoners from the Mittelbau-Dora concentration camp, some barely clinging to life, who had been enslaved to build these so-called vengeance weapons. Major James Hamel of Army Ordnance walked through the tunnels in a growing state of disbelief. The Germans had been producing V-2 missiles at a rate of roughly 600 each month. Each rocket required around 50,000 individual parts. The level of precision machining, the rigorous quality standards, and the logistics required to keep production flowing in these subterranean facilities represented an industrial accomplishment that seemed impossible for a nation supposedly collapsing under the weight of defeat. But Hamel recognized something many frontline troops did not. These rockets were far more than just advanced weapons. They were the keys to the future, and the Soviets were closing in. Their occupation zone would include this territory within weeks. Every document, every machine, every rocket would soon be in Soviet hands, unless the Americans moved quickly. Urgent orders from Washington soon reached Colonel Hoftoy. Secure the rockets, seize all documents, and remove everything before the Russians arrived. This mission, known as Special Mission V-2, became one of the most crucial intelligence efforts of the final days of the war. American soldiers worked night and day loading trains, 341 rail cars packed with V-2 components, enough to assemble about 100 complete missiles, along with thousands of pounds of technical records. All of it was rushed to the port of Antwerp, where Liberty ships waited to transport this remarkable prize across the Atlantic. By late May, the first of these captured parts reached the White Sands Proving Ground in New Mexico's Tularosa Basin. There, Army engineers began opening crates and sorting documents, and with every new discovery, the scope of German advancement became even more startling. The V-2, officially labeled the Aggregate 4, stood 46 feet tall and weighed nearly 28,000 pounds at launch. It could deliver a warhead weighing a ton to targets more than 200 miles away with reliable accuracy. Yet these headline characteristics revealed only the surface of its significance. The true shock came when American scientists disassembled the rocket piece by piece. At its base, they found a powerful engine, a massive combustion chamber generating around 60,000 pounds of thrust. To U.S. experts familiar with Goddard's prototypes, this figure was astonishing. After years of work, Goddard's most powerful liquid fuel engine had achieved just under 1,000 pounds of thrust. The Germans had built an engine roughly 60 times stronger and were manufacturing it in quantity. Among the first American scientists to analyze the rocket was Dr. Theodor von Karman, head of the Jet Propulsion Laboratory at Caltech, and what he observed left no doubt: Germany had reached the future first. Von Karman's team had been working on rocket propulsion for the U.S. Army since 1942, developing what would later become the Corporal missile. Yet when he examined the V-2 engine, his assessment was delivered without hesitation. The United States was at least 7 years behind Germany's technology. The V-2's propulsion design alone incorporated multiple breakthroughs far beyond American progress. Its combustion chamber used a double-walled configuration in which alcohol fuel circulated through the outer layer before being injected into the chamber. This design simultaneously cooled the chamber walls and preheated the fuel supply, solving one of rocketry's most fundamental engineering challenges, preventing the chamber from melting under combustion temperatures that soared to 5,100 degrees Fahrenheit. But it was the turbopump system that most astounded U.S. engineers. Positioned at the core of each V-2 was a steam-powered turbine spinning at 4,000 revolutions per minute. This turbine drove centrifugal pumps that fed the combustion chamber with liquid oxygen and fuel at a rate of 125 liters every second. The turbine produced a tremendous 600 horsepower and had to pump super-cold liquid oxygen at approximately -297 degrees Fahrenheit, while operating under pressures that would destroy pumps built using ordinary American manufacturing methods. The Americans regarded this machinery with a mixture of admiration and dread. The turbopump represented 7 full years of dedicated German development, progress in metallurgy, machining accuracy, and mechanical engineering that simply did not exist in the United States. The turbine blades were formed from advanced nickel-chromium alloys capable of surviving both unimaginable rotational stress and extreme temperatures. The pumps incorporated seals engineered to prevent cryogenic oxygen leaks even while rotating at speeds where the slightest imbalance could cause catastrophic destruction. Navy engineer Lieutenant Commander Robert Truax, who investigated the V-2 propulsion system, explicitly stated in his report that the German turbopump did not merely surpass U.S. capabilities, it relied on knowledge and materials America entirely lacked. He concluded that building a comparable device would require new alloys, new manufacturing techniques, and new industrial processes, and estimated that even with unlimited funding and ideal access to scarce resources, it would likely take a minimum of 18 months just to produce a single operational prototype. The rocket's guidance system delivered yet another unsettling revelation. The V-2 relied on an analog computer, the Mischgerät, developed by Helmut Holzer, which constantly processed data from gyroscopes and accelerometers to steer the rocket during flight. 2 free-spinning gyroscopes measured pitch, yaw, and roll, while a pendulous integrating gyroscopic accelerometer, the first ever deployed, measured acceleration and mathematically integrated it over time to calculate the rocket's velocity.
Once that velocity reached the programmed value, ordinarily around 3,500 miles per hour, the system automatically shut down the engine. This level of sophistication astonished American specialists. The gyroscopes, produced by the German firm Goddard, were built with a precision American industry could not equal. The analog computer handled multiple simultaneous data streams, controlling 8 separate aerodynamic and jet stream steering elements, 4 rudders embedded in the tail fins, and 4 graphite vanes inserted into the exhaust. These internal vanes, subjected to exhaust temperatures over 5,000 degrees, were made of special graphite capable of surviving the intense heat while maintaining precise directional control in the rocket's crucial first minute of flight. Dr. Charles Stark Draper of MIT, America's most respected leader in guidance research, examined the German system with considerable professional admiration. Though he had spent years advancing gyroscopic controls for aircraft and submarines, Draper immediately recognized innovations his team had not yet imagined. The Germans had solved the core problem of integrating acceleration into velocity, creating a guidance system that actively commanded the rocket's flight in real time. Draper identified it as the first true electronic active control system ever fielded on any vehicle, a technology essentially equivalent to fly-by-wire systems that aviation would not widely adopt for decades. Yet perhaps nowhere was the technological gulf clearer than in manufacturing standards. U.S. inspectors studying the V-2 parts discovered machining tolerances more precise than those found in American commercial industries during peacetime. Welds showed flawless craftsmanship. Mechanical tolerances were measured to within thousandths of an inch. Components experiencing high loads were consistently over-engineered with large safety margins. Design decisions American engineers, constrained by wartime materials shortages, would never have approved. One U.S. Army ordnance officer, while reviewing the turbopump assembly, observed that every component appeared designed to endure worst-case combat scenarios. Fuel lines were equipped with redundant paths. The electrical circuits carried far more breakers than strictly required. The frame and shell were noticeably heavier than the minimum theoretically necessary. This was engineering based on industrial abundance and confidence, not improvisation under scarcity as seen in American designs. Even the electrical systems displayed complexity beyond American work. The V-2 used a 24-volt power system with generators driven both by the main turbopump and a separate auxiliary turbine. American rockets, when they featured electrical systems at all, typically used single-generator 12-volt setups. Meanwhile, the V-2 hid 8 miles of carefully organized wiring, precisely bundled and secured to prevent damage under extreme acceleration.
The V-2's electrical network also powered motor-driven valves, gyroscope systems, ignition components, and real-time telemetry capable of transmitting data during flight. When Robert Goddard examined the V-2 that afternoon in Annapolis, he instantly recognized the similarities to concepts he had pioneered: liquid oxygen and alcohol propellants, centrifugal pumps powered by turbines, gyroscopic stabilization, and exhaust vanes for directional control. In a letter to his benefactor Harry Guggenheim, Goddard expressed frustration beneath a thin veneer of professionalism. He wrote that the Germans had effectively used his patent ideas, taking principles he had introduced and executing them at a scale he could only dream of. The V-2 represented the kind of rocket he believed he could have built himself if he had ever received true national support. Yet Goddard, despite his genius, failed to grasp a crucial distinction that many other U.S. engineers quickly understood. Germany had not copied American research. They had independently constructed a rocket development program that by 1945 had advanced nearly a decade beyond American work. Hermann Oberth's theoretical contributions paralleled Goddard's ideas. Werner von Braun's group at Peenemünde began experimenting with liquid fuel rockets in 1932, advancing on their own scientific foundation. By 1934, their A-2 rocket had already exceeded the highest altitudes Goddard had reached. The German effort was backed by the state, prioritized by their military, supported by top universities, and employed thousands of skilled scientists and engineers across multiple disciplines. Goddard's personal altitude record was 9,000 feet in 1937. The A-4, later known as the V-2, routinely climbed to 50 miles, pushing into space before descending onto targets over 200 miles away. His most powerful engine produced 985 pounds of thrust. The V-2's engine delivered 60,000 pounds. Goddard worked with a tiny team in remote deserts, funded by a private foundation and largely ignored by the U.S. government. Germany operated an enormous research and production complex at P&M&A, with a level of national investment comparable to what the United States devoted to the Manhattan Project. The comparison wasn't simply Germany versus America, it was an entire industrial superstructure focused on rocketry versus one brilliant individual with minimal backing. By June 1945, after extensive analysis of captured V-2 rockets, a unified view formed within secret War Department reports. The United States faced a dangerous strategic disadvantage. Ballistic missiles were clearly the future of military conflict. Germany had proven that targets hundreds of miles away could be hit without warning and without any means of defense. Meanwhile, the Soviet Union had seized P&M&A, taken over the production infrastructure, and captured thousands of German rocket specialists. Without urgent action, the United States risked falling hopelessly behind in the most important military technology of the coming era. This realization directly triggered Operation Paperclip, one of the most morally difficult decisions made after the war. In September 1945, von Braun and 126 members of his rocketry team arrived at Fort Bliss, Texas, under military supervision. These scientists had built Hitler's terror weapons. Many had exploited concentration camp prisoners as slave labor. Their rockets had killed civilians across London and Antwerp, but they also possessed irreplaceable knowledge America desperately needed. The ethical dilemma was significant. These men included Nazi Party members and SS officers whose work caused thousands of deaths. And the underground factories where V-2s were built killed more forced laborers than the rockets killed victims in combat. Yet the Soviet Union was already reconstructing German missile development under Helmut Grootrup with its own captured specialists. The Cold War was beginning, and the United States could not afford to fall behind. At White Sands Proving Ground, captured V-2s were soon reassembled for testing. A static firing occurred on March 15, 1946. The first launch, on April 16, lifted off at 2:47 p.m. and almost immediately failed. A fin detached, guidance malfunctioned, and the rocket crashed after reaching only 3.4 miles in altitude. The moment was sobering. Even with German rockets and German engineers, America lacked the industrial experience and accumulated knowledge that came from Germany's 6,000 test and combat launches. Colonel Harold R. Turner summarized this stark reality, stating that Americans now had the hardware and the designers, but not the production heritage or the institutional expertise that had made such rockets possible in the first place. Germany had years of practical trial and error behind them. The United States was starting from scratch. In the years that followed, 67 captured V-2s were launched from White Sands, with mixed outcomes. About 68% were called successes, an unacceptable failure rate by combat standards, but invaluable for learning. Each flight advanced American understanding of propulsion, guidance, high-altitude aerodynamics, and missile-grade engineering. Universities, military research groups, and emerging aerospace firms used V-2 launches to carry scientific instruments, cosmic ray counters, atmospheric probes, and even cameras. On October 24, 1946, a V-2 lofted a 35mm camera to an altitude of 65 miles, capturing the first photographs ever taken of Earth from space. The grainy images, showing Earth's curvature, were a world-changing milestone, proof that rockets could reach space and return useful data. Yet using German-built rockets was only a temporary measure. The ultimate goal was to construct an American rocket era. In 1948, the Army Ordnance Department selected Redstone Arsenal in Huntsville, Alabama, as its new permanent missile center. Von Braun's team moved there, partnering with American engineers to develop new rockets based on V-2 lessons, but designed for U.S. needs. The first major product of this collaboration was the Redstone missile, directly inspired by V-2 technology, still using liquid oxygen and alcohol propellants, turbopump systems, and gyroscopic guidance, but improved with better efficiency, more reliable electronics, and Americanized manufacturing standards. By the mid-1950s, the technological gap was finally narrowing. The Jupiter, Thor, and Atlas missiles represented homegrown American rocket engineering, built with domestic materials and industrial capability. When the Soviet Union shocked the world by launching Sputnik in October 1957, the United States quickly answered with Explorer 1 in January 1958. It was launched atop the Jupiter C, a rocket derived directly from the Redstone lineage. Later, the Saturn V that sent astronauts to the Moon in 1969 was engineered by Wernher von Braun's team at NASA's Marshall Space Flight Center. Its colossal F-1 engines each produced 1.5 million pounds of thrust, more than 25 times the output of a V-2 engine. Yet the technological ancestry remained unmistakable. Regenerative cooling, turbopump propellant delivery, thrust vectoring through movable engines, and sophisticated guidance systems. All ideas introduced and proven in the V-2, now matured and expanded to finally achieve the dreams Goddard once championed, concepts that German engineering had demonstrated could be real. Viewed today, the legacy of the V-2 is deeply conflicted. It was a terror weapon that inflicted immense suffering while offering limited military benefit. Its construction relied on slave labor, making it a symbol of one of the many horrific crimes committed during the Second World War. At the same time, it was the first operational ballistic missile, the first human-made object to cross into space, and the technological origin point for rockets that would ultimately carry satellites, probes, and people far beyond Earth. For the American scientists who first examined captured V-2s in 1945, the moment was both humbling and alarming. The United States, a nation of unmatched industrial strength and scientific talent, had been left years behind by a country it had just defeated. Goddard's groundbreaking work had gone underfunded and undervalued, while Germany had poured enormous national resources into advancing similar ideas. The takeaway became a guiding principle of U.S. science and defense throughout the Cold War. Maintaining technological superiority demands long-term investment, strong institutional backing, and recognition that individual brilliance alone cannot compensate for national inaction. When NASA inaugurated the Goddard Space Flight Center in May 1959, Administrator T. Keith Glennon honored both Goddard's genius and the uncomfortable lesson his career revealed. Goddard dreamed of reaching the Moon, but his rockets climbed no higher than 9,000 feet. German engineers, working independently and with massive support, succeeded in reaching space. The modern American space program rests on both foundations: Goddard's pioneering vision and the stark reminder that vision must be matched with resources and national resolve. Ultimately, the V-2 provided three fundamental lessons to the United States. First, rockets would define future military power and open the gateway to space. Second, technological leadership could be lost through neglect and regained only by sustained effort. Third, in the coming Cold War, supremacy would belong to the nation that controlled space and possessed long-range missile dominance. Those American engineers who stood over that first V-2 in the spring of 1945 saw all of this, even if they could not yet fully express it. They recognized the gap between America's abilities and what the future demanded. They saw the price of ignoring innovators like Goddard,
and they saw that the future of technology was sitting before them in German hardware, waiting to be studied, mastered, and surpassed. The Annapolis warehouse, where Goddard inspected the V-2, is long gone. But the moment endured. The revelation that the United States had fallen dangerously behind sparked a national commitment to rocket research, a commitment that would lead just 24 years later to American astronauts walking on the moon. Germany built the V-2 as a weapon of vengeance. For the United States, it became something entirely different, a wake-up call, a teacher, and a challenge to push further. The fact that America ultimately exceeded what the Germans achieved, constructing rockets capable of taking humans beyond Earth's orbit, proved that technological gaps can be closed. But doing so requires acknowledging the gap, dedicating resources to overcome it, and understanding that those who fail to invest in the future will inevitably be surpassed. When Wernher von Braun stood at Cape Canaveral in July 1969, watching Apollo 11 rise atop the Saturn V toward the moon, he reflected on the journey from Peenemünde to the Sea of Tranquility. The science had always been understood, he noted, even in the 1930s. What changed was not physics, but determination. America succeeded where wartime Germany could not. It mobilized an entire nation to reach for the stars, as an act not of destruction, but of human achievement. That determination began in places like that warehouse, where American engineers scrutinized captured rockets and confronted an uncomfortable fact: the United States was years behind. The only question was whether the country had the will to close the distance.